This is Statistics 243 at Berkeley for Monday, November 3rd.
Hi. Do you mind if she comes? She's visiting some of her friends.
Yeah, that's fine.
See you class.
All right, let's go ahead and get started. Let's see, so a couple things. I'm going to solicit your feedback on problem set 6 and the trade-off between things being a pain in the ass and things being worthwhile. So it was a bit of an experiment. I hadn't done the material in that level of detail or had a problem set on it in the previous years. And it was a lot of work for me as well, so I share your pain. So I might wait for a couple days so any pain can sort of be dulled a little bit. But I'll probably send out a little survey sometime later this week and see what people think about how it went, whether it was worthwhile, potential improvements if I do something like that again next year. Let's see, other assorted items. We have maybe a day and a half or 2 days left on the linear algebra material, and so what's going to happen today is I will talk through the QR decomposition and some of the methods that are used to get the QR decomposition in some detail. And as a result of that, partly the reason is the goal is not to sort of overwhelm you or bore you to death with different ways of doing the QR decomposition, but by virtue of doing the QR decomposition in a few different ways, we'll see some different techniques that come up in some other linear algebra contexts, namely doing reflections that are called householder reflections, and doing rotations, which are called Givens rotations, and Graham-Schmidt orthogonalization. And then I'll say, maybe not today, I'm not sure, but maybe on Wednesday, I'll say some things about, a little bit about computing the eigendecomposition and computing the SVD, and then I'll spend a bit of time on sort of giving an interpretation of what an SVD does in a statistical kind of context. And then either towards the end of class on Wednesday or on Friday, we'll start in on the simulation unit, which will mainly be about thinking about how do you think about simulation studies, how do you generate random numbers on a computer, and maybe a couple other things that I'm forgetting about. Okay, so picking up from last time, I had given this example where I did pivoting with the Cholesky, and somehow or another there ended up being a bunch of ones on the diagonal of the block that I thought was going to be all zeros. So I didn't actually get a chance to figure out what was going on with that, but I did get a simpler example to illustrate more what I thought was going to happen, and I thought I would just show you that. So what I'm going to do here is I'm just going to create a matrix that is singular and basically has a constraint built into it. So if I look at this matrix here, this is a covariance matrix, but it's a covariance matrix where the first x1 has a 0.2 correlation with the second x2 and x3, but x2 and x3 are perfectly correlated. Okay? So if I did an eigendecomposition on this, I would get that there was the last eigenvalue was 0. Okay? And that also means that I shouldn't be able to do a Cholesky decomposition without having to deal with the fact that I might end up either taking the square root of 0 if I were able to do this precisely, or taking the square root potentially of a very small negative number, and then the algorithm breaking. So if we actually go ahead and do this, what you'll see is we get this warning message. It did actually complete with the pivoting. And if we look at it, what we see is, I'm not totally sure why this is showing up not as an exact 0, with the algorithm having basically injected an exact 0 when it got to trying to fill this in, but it fills it in as basically numerically 0. Okay, so that shouldn't be too surprising that we're getting something that's essentially 0. So this fits with what I said last time, with basically if I think about the fact that there's a redundancy in this covariance matrix, that two of the three variables are perfectly correlated with each other, it makes sense that I end up with a 0 down here in this the lower chunk of the matrix, which in this case is just the 3-3 element. And then the other thing that comes up when we do this, well, just to demonstrate to you that this does indeed recreate. If I take the transpose of u times u, I do indeed get back the original matrix, so it is a legitimate Cholesky decomposition in that sense.
Is there a reason for column scientific notation?
That's a good question. This one here. I don't know whether. Oops. So it looks like these are just estimates. It looks like these, when the arithmetic gets done to compute the first column, it looks like those are exactly 1 and 0. Presumably it can actually just do the arithmetic exactly in base 2. I think in terms of the second and third columns, I think it's just a matter of sometimes, I don't know exactly what the rules are of when R decides to switch over from just writing out all the decimal values to switching over to scientific notation.
I have an idea, maybe.
Yeah.
Because it has to show that small close to 0 value in scientific notation, because it's small order of magnitude, it might like coerce the other ones in the other values in the column.
Yeah,
Is
that's
it also being shown in scientific notation.
yeah. I think that's a nice thought. I mean, right, the usual column. The idea that R works with columns, so that if it has to do the third element of that third column, then the others are shown that way. Yeah. So I think that's probably reasonably on target there. Okay, so then the other one I wanted to show was this one. I'm just going to reorder the rows and columns of the matrix so that the first and second of the variables are the ones that are perfectly correlated. Oh, okay. So now this gets a little more messy because I still have the digits set equal to 22. Okay, that's better. Okay, so now first and second ones are perfectly correlated. If I start to walk my way through the Cholesky decomposition, when it gets to trying to find the two elements of the factorized matrix, that's where it's going to run into the numerical trouble of trying to do the square root of something that might be negative. So in this case, it's going to have to do what I said last time, which is it's going to have to do some reordering like we saw with the LU decomposition. And we should see that in the resulting pivoted Cholesky matrix. Okay, so now if we look at U, we see, okay, what it seems to have done is it has indeed put a 0 in this 3-3 position. And we would have expected that 0 to be in the 2-2 position because it's the first and second variables that are redundant. But it's done some reordering, and the fact that it now says that this attribute is 1, 3, 2 basically indicates it's done that reordering, because this is not a 1, 2, 3. It basically shows what the ordering has to be to recover things. And if we tried to take U transpose U and reconstruct the original matrix, and we just take the U as it is here, given the fact that we were just talking about there being things being out of order, it shouldn't surprise you to see that when I just do U transpose U, I get back something that is indeed essentially the original matrix, but it's with the rows and columns permuted. Okay. So basically the Cholesky that's being done is a Cholesky on this matrix where things have been reordered and such that the 0 piece gets pushed down to this lower corner of the matrix. So this is basically what I was expecting to see with that other example, which, as I said, I haven't actually had the time to figure out why that wasn't working the way I expected to. But this is sort of more the behavior that I was expecting. And the point of going over this was just to show you an example where it actually worked out, and to just reiterate this idea that if you were to work with this Cholesky matrix once the pivoting has been done, you need to pay attention to the ordering, because you're not going to have the ordering that you're not going to have the original ordering, and you have to do some permuting yourself to deal with it. Okay. Any questions about that? All right. So let's see where we were in terms of the QR decomposition. So we had talked about this idea of why the QR is used for doing regression, which is that if we do the QR on X instead of first computing X transpose X, it gives us this nice representation. We have some cancellation of the two Q pieces from the X and the X transpose. And then we end up directly, as soon as we've done the QR decomposition, we end up directly with an upper triangular system of equations. And that's easy to solve for reasons that we've now discussed sort of ad infinitum. The other point that gets made in why sort of justifying why to do the QR decomposition is the following fact, which is that the condition number of x is the square root of the condition number of x transpose x, or as I wrote it up there on the board, the condition number of x transpose x is the square of the condition number of x. So what I thought I'd have you guys do is just, and this sort of gets us to start thinking about the SVD, which is where we're headed in maybe another class or so, and about the relationship of the SVD to an eigendecomposition in problems like this. So what I'd like you to do is take 30 seconds or a minute, consult with your neighbor, see if you can figure out why it is that this is true, and you will want to make use of the fact that we can decompose x into this UDV transpose, which I've also written up here. So if you can sort of try working with that, and you should see that just as we know that the condition number we can usually get based on the magnitude of the largest and smallest eigenvalues, and here we're going to end up working with the squares of those eigenvalues. So see if you can work that out, and we'll reconvene in another minute or so. Alright, remember we have, what was it? I'm going to get this right off the top of my head. We had the accuracy as the condition number. So if we're solving AX equals B, condition number of A times basically 10 to the minus 16 when we're working on a standard computer. And this was the ratio of the largest to the smallest eigenvalues of A. And just as a reminder, we can always do, I guess I didn't write it over there this time. If we have symmetric A, we can always do that. All right, Chi, do you have any thoughts? Aurelia, are you here? All right, Wang, are you here? Okay, good. Yang, are you here? Yes. Any thoughts? No? All right. Anybody else? Yeah.
Plug in the secret value decomposition into x transpose x.
Yep.
You see that the eigenvalues of x transpose x is squared with the eigenvalues of x.
Okay, so we've got x transpose x, and you're saying plug in the SVD.
Right? So UDV transpose.
Okay, so UDV transpose UDV, right? This is the transpose, D transpose, but D is diagonal, so it's just D. U transpose U, D, D. What's this? Identity matrix. So we have this is V transpose D, V squared. There's a D squared here. Okay. So if we look at this and now think about what an eigendecomposition is, well, it's just a diagonal matrix in the middle, and we have an orthogonal matrix, the eigenvectors on either sandwiched around it, right? So this is just, we can get the eigendecomposition of x transpose x by doing an SVD, and then just knowing that these things are actually even called the right eigenvectors. And these things are called the left one, the left eigenvectors. It sort of makes sense that they're called that, both because these two pieces are, or orthogonal, but also because if we work through this for x transpose x, we actually get that the v's are the eigenvectors for that cross product matrix. Okay, so now we've got a d squared in here, so all the eigenvectors, all the eigenvalues are squared, so it makes sense that when we were talking about the condition number originally, we were talking about the ratio of the largest and smallest eigenvalues. Well here, if we do x transpose x, we're talking about the ratio of the largest and smallest eigenvalues squared. If we actually start with x and then do x transpose x. So that's sort of a numerical perspective on why it's a good idea to do, if you're trying to solve x transpose, if you're trying to compute x transpose x inverse x transpose y, that's sort of a numerical argument why it's good to do the QR on x and then work with the QR decomposition, as opposed to computing x transpose x and then directly doing the Cholesky decomposition on it. Because the Cholesky decomposition would be being done on a matrix whose condition number is rather bigger than the condition number if you were working with the QR decomposition. Okay, so now that I've said that, I'm going to say why does it really? I'm going to make an argument that it actually doesn't really matter. So the argument is basically what I say here. So if we think about when we're going to have a large condition number and when it's going to be hard to get, it's going to be hard to solve that system of equations or invert the matrix accurately. The situation is basically going to be, as we've already talked about, it's going to be when columns of x are essentially collinear with each other, when they're basically, when you can express one column of x as a linear combination of other columns of x. So there's a redundancy in the variables that you're using in your regression. Well, if that's the case, yes, you might have numerical problems, but you're going to have statistical problems in the sense of you're going to have a lot of uncertainty in estimating the beta for a given variable because you don't know whether the association between the response and that variable is due to that variable or to the other variable that it's highly correlated with. So my sense of this is long before you get to sort of issues of whether you can compute this numerically very exactly, your statistical uncertainty is going to increase a lot because of the fact that this trading off means you really can't identify which of the variables are the ones that are associated with the response. And so there's basically going to be trading off and uncertainty, a lot of uncertainty because of that. So it's not totally clear to me that it really matters, this sort of numerical argument matters in terms of whether you did ordinary least squares with a Cholesky decomposition or a QR. But this is one reason why folks do it with the QR. Okay. All right. So another thing we could think about is we have these different ways that we could solve the least squares problem, and this is really only going to be relevant if we have a lot of covariates, because otherwise, if we have a 10 by 10 x transpose x matrix, it's going to be trivial to do the computation quickly, regardless. But if you actually write out what the amount of computation is to solve least squares with Cholesky, it looks like this. There's another algorithm that we're not going to talk about that's called sweeping that looks like this. And then there are different ways of doing the QR decomposition, and those different ways have different computational complexity. So if the first one we're going to talk about in a few minutes is this householder method, and that involves this, and the Graham-Schmidt involves this. So you can see that all of these involve sort of different ways of playing around with the constants in front of the np squared, and sometimes having a p cubed term. And so based on looking at that, you could say, well, depending on how big n and p are relative to each other, one of these might be more computationally efficient than the others. And for your given problem, you could try and think about which of these makes more sense. But it's really only going to be relevant if p is really quite big. So it's not necessarily something that you would have to think about in many situations unless you're dealing with really high dimensional regressions. Okay, any questions or comments? All right, so let's talk about a couple ways of computationally doing the QR decomposition. I have a little bit here in terms of if you were doing the QR and R, what it returns back. And basically, if you really wanted the Q matrix or the R matrix, you can get it using these methods. So the QR function will basically spit back an object, an S3 object. And if you actually wanted the QR matrix or the R matrix, you basically need to pull it, extract it out of this object using a method that works on that kind of S3 object or that kind of S3 class. And there are also methods, if you really wanted to use, if you wanted to multiply Q times something, you can use this method QY that again uses this object that is computed as the result of doing the QR decomposition. So there's a lot of this object-oriented stuff built into doing these QR decompositions. Okay, so let's talk about a few of the ways of computing the QR decomposition. And it's basically the strategy, the game here is again sort of what we've been talking about in other contexts, which is you have some matrix, you're trying to transform it into some upper triangular form. So what is it that you need to do? You need to be injecting zeros into this matrix in one way or another. And so what we're going to see is a few different ways of getting the zeros into the matrix. And in each of those cases, the operation that injects the zeros into the matrix is going to be equivalent to applying an orthogonal matrix to the original matrix. So the result, you apply a bunch of orthogonal transformations to the original matrix, you get out a triangular matrix as a result, and then the Q matrix of the QR is the product of those orthogonal transformations. So that's sort of the basic strategy. Okay, so to motivate the first one, which is these householder reflections, the idea is, just going back to sort of two-dimensional geometry, suppose I have some vector x, and I define a coordinate system based on these vectors u and v. I can reflect this vector x across the v dimension of this uv dimension, of this uv coordinate system, and I'll get this matrix x tilde. Okay. And it turns out that can be done with an orthogonal transformation Q, and the matrix Q that does this is a matrix that is constructed like this. It's the identity matrix minus 2 times the U vector times the U vector transpose. So this is just an outer product, and it'll create a matrix, and then we do the subtraction of the two matrices. And so this matrix Q is orthogonal, and the result of applying to X is to produce this X tilde vector. So that's called a householder reflection. The Q matrix is called a householder matrix. And okay, well that just might be sort of a nice mathematical result, but for our purposes here, we want to relate it back to this idea of injecting zeros into the matrix. So the way that we can think about it is, now suppose I have this vector x. I basically want to transform this vector x to be this vector x tilde. And why do I want to do it? Because if I think about the fact that I'm starting with a matrix x, and let's just take one of the columns, my whole goal here is to make this, I'm trying to take this matrix and make it into an upper triangular matrix. So my whole goal is to take this matrix and replace this first column with a number here and then all zeros. Right? Well, one way I could do that, and this is just in 2 dimensions, but you can imagine there's just a generalization of this will work in higher dimensions, is if I can do a reflection that gets this vector transformed into this vector, well, now it's axis-oriented. So it's only going to have a value that's non-zero in the first position, and this two-dimensional representation will just be a 0 here, but in the higher dimensions you'd have zeros in the other dimensions. So what do I need to do? Well, I basically need to choose my UV coordinate system such that the reflection is such that this thing gets reflected across the V dimension to get onto the axis-oriented position. Just like over here, I just sort of had an arbitrary reflection, and this was being reflected across the V dimension there. Questions about that? Okay, so let's see. As usual, I'm struggling with board management. Okay, so folks who recognize that this would be a potentially useful strategy realized, okay, so you can take Q to be I, U transpose, and in order to do the one where we get it onto the axis-oriented directions, we're going to set U to be equal to X minus the X tilde that we want over the length of the difference between those two vectors. And X tilde, the X tilde we want is what I wrote over there. It's basically the length of the X vector and then as many zeros as we need given the size of the matrix that we're working with. So this would be the nth dimension if we've got an n by p matrix X. So it sort of makes sense that this U vector could be defined by taking X minus X tilde, because if you think of this X tilde, we take minus of X tilde, that's going to be this vector, and you can sort of see that sort of roughly looks like it works out geometrically to get us this U, and then it sort of makes sense that the V is orthogonal to that, and that gets us to where we want to be. Okay, so what is this? And if you actually worked through, it's not hard to work through and show that if you take Q, this particular Q from this particular U, and apply it to a vector X, that you are going to get the X tilde that we are looking for here. So then we can think about what's our strategy for doing the QR decomposition. So I'm going to take some Q1 times my matrix X. And what that's going to do is that's going to give me a matrix where I have let's see, I guess I'll just call this X dot 1. And I'll call this R1, and I'll call this X super 1. Okay, so I do this business up here. That business is designed to zero out these elements of the first column vector of the X matrix, and the result, and the Q1 is the Q up here. That's an orthogonal matrix. So the result is I've injected these zeros into the matrix, and now you can just sort of keep playing the game, sort of like we did with the LU decomposition, where now we're going to focus on this sub piece of the matrix. Now we're going to focus on this sub piece, and so on and so forth until I've zeroed out all of the stuff below the diagonal. So Q2 is going to be designed to zero out. It's going to be designed to zero out those elements of this partition of the matrix. So Q2, you can work it out. It's not hard to work out. It has to look like this, and then I guess the notation I was using is it's going to be Q2, 1. So just pull out this matrix, do the same thing we did here, but in an n-1 dimensional setting, where we now construct Q2, the sort of next iteration for Q2. And then the overall Q2 to deal with the full n by n matrix just has a 1, 0, 0, and 1, 0, 0 here. Okay, the result of that, so the result of doing Q2, Q1, X is now going to be, and then zeros, and then it's going to be this I'll call it x21, zeros, and now I've got x superscript 2 down here. And I'll call that R2 with this. Okay, so you just keep playing this game, and you end up with Qn Q2 Q1 times x equals R. That is the R. That's an upper triangular matrix. It is the R in the QR. Sorry, it is the R in the QR decomposition. All of these guys, you can show, pretty easy to show. All of these guys are orthogonal matrices. You multiply them together, you get another orthogonal matrix. And if I want to then get the QR here, I take the inverse of that. And so I've got that x is the inverse of Qn Q1. But of course, all of these are orthogonal, so the inverse of each one of these is going to be the transpose of it. So it's going to look something like Q1 should look something like Q1 transpose up to Qn transpose R. And there's our Q. All right, any questions about that? All right, a little computational question arising out of this. If I wanted to compute, say, Q1 times x efficiently, let me just see how I want to frame this question. Yeah, let's just frame it as Q1 times a vector x. Suppose I had one column of my x matrix, and this is just a vector. If I had a full dense matrix Q1 and I multiplied it, that was n by n, and I multiplied it by an x vector that was of length n, how many computations am I doing?
N squared.
Squared. So that's n squared computations. Okay, so look at this for 30 seconds or a minute and think about how I can make sure that I'm not doing anywhere near this many computations, knowing what I know about what Q1 looks like. Okay, so what would I do? What would I do here? Say it again. So you're saying decompose x into some C1u plus C2 v? Okay, and then what would you do?
Find Q,
Okay,
and you can pull out constant. And you know QU is minus U and QB is 3.
and you know QU is, okay, so yes, you could, okay, so that's interesting, I hadn't thought of that. So, that's great. So I guess then the question is how much computation we would need to do to find those guys. Okay. So that might actually be essentially the same amount of computation as the way that I was thinking of it. We'd have to sort of just work through the details, but that would be a useful thing to try out. Other possibilities? What do I know about Q? Okay, what else do I know about Q? How did I construct Q?
Orthogonal matrices.
Huh?
The orthogonal matrices.
Okay, but how did I construct it up there, here? Right, I didn't construct X, I didn't construct Q originally really as a matrix. I mean I did, but I constructed it from vectors. Right? I constructed it as an outer product. So there's a lot of structure to Q that comes from having constructed it as an outer product. So if I think about this Q1 is just that Q, it's just changed the notation. So I have I minus U transpose X. Right? This is I times X, so that's obviously just X, right? Minus U transpose X. What's that in terms of how many computations I have to do? Yeah. Yeah, it's just n computations. This is a vector. This is a vector. And this is just vector-vector multiplication. Okay, this is just an inner product. So the n computations there. I have some new vector as a result of that. And I also have a vector U here. Right? So if we think about what this looks like, this okay, so what does this look like? I like to draw things out geometrically. The outer product of U times itself looks like this, and now I've got some vector X that's being multiplied by it. Okay, so now I do U transpose times X. That's just going to be a number, right? And so now I have a vector just times a number, right? And so that's also just going to be another n computations. Then I have to do a subtraction from the original vector X. But I've only done 2n computations here compared to n squared. And it might very well be, I suspect that it would be, that Tiani's suggestion would turn out to be basically the same amount of calculation. We'd have to work through the details. Okay, so part of the reason I wanted to point this out was anytime you know that some matrix you're working with is constructed in some structured way, and you know how it's constructed from sort of simpler, lower dimensional pieces, that's usually an indication that there's probably going to be that there may very well be a quicker way to do the computation than just going with blunt force and just computing this by doing the matrix vector or matrix computation. All right, questions or comments? Okay, so that was the reflections approach to doing the QR decomposition. I'll say a few words about something called Givens rotations, and it looks like we'll do Graham-Schmidt next time. Okay, so let's go back to the sort of motivation from basic geometry. When I did the reflections approach, I was saying, okay, let me create this vector, let me create this new set of directions or dimensions or coordinates. I'm going to reflect x across that to get to x tilde so that I can zero out some of the values, and I can zero out all but one of the values in one of the columns of the x matrix. Well, another way I could think about this is another way that I could do this is I could rotate the vector x so that it's axis oriented. Okay. And if this angle is theta here, just in two-dimensional space, this is a elementary rotation matrix. If I use the matrix Q and apply it to x, that will also give me an x tilde like we had before, where it's axis oriented. Okay. So in order, if we know what theta is, we construct Q like this. If we're having to figure out what theta is from those vectors and doing the trigonometry, it ends up being this, where x is just x1, x2. It turns out this thing is also an orthogonal transformation. This is also an orthogonal matrix. Okay, so now the question is, how does that help us in this larger problem where we have more than 2 dimensions? So the basic story is suppose I have x, and that's x1, x2, xp, xq, xn, and I want to take that and I want to inject a 0 in the xq position to make this a matrix like this. So basically I want to do what I was doing over there in a 2-dimensional subspace such that I zero out this one of this pair of the dimensions. And it turns out, this is also not hard to show, that all I need to do is basically take that 2x2 matrix and insert it into an identity matrix to do this. So the Q matrix that I need looks like an identity matrix, except I've got in the pth position, I have the cosine of theta, and then in the pqth position I have minus sine of theta. Sorry, is that minus or plus? Plus. And then I have minus sine of, sorry. Down in the qpth position I have minus sine of theta, and then I have cosine of theta. And then otherwise I still have 1s on the diagonal and 0s everywhere else. Okay, so that matrix will basically rotate in this 2-dimensional subspace and inject a 0 in this position, the qth position of this vector here. And it shouldn't be surprising to then see that the strategy here, am I on the right page? Yeah. Is we now just need to apply a ton of these transformations, because I need to basically in the reflections approach I was able to zero out a whole bunch of values at once, but here I'm zeroing out one value at a time. So I'm going to let's see, so when I do Q1 2 times x, I'm going to start with my original x matrix. But just sort of more evocatively in our usual n being bigger than p. I'm going to zero out this position there with Q1 2, the 2, 1 position. Now I'm going to apply Q1 3 to it. That's going to zero out this position all the way on down to Q1n. That'll zero out this position. So that's this piece of the transformation, and then I'm just going to keep doing that. I'm going to get a Q2 3. That's going to zero out. Let's see. So I've got a value here, a value here, a value here. I'm going to zero out that position with Q2 3, and I'm just going to keep going like that. And then the story is going to be the same as we saw with the householder reflection approach. At the end of the day, I've applied all these transformations. I've injected all the zeros into that matrix over there. And so the result is an upper triangular matrix X. But again, all of these are orthogonal transformations. So I can just take the inverse of the entire set of entire product of matrices. And the result is the Q that I want for the QR is going to be that transformation of that transformation of these orthogonal matrices. Okay, any questions about that? Okay, so part of the reason that I went into all that, we're going to talk about Gram-Schmidt a little bit next time. It won't take us too long. It's just another way of injecting a bunch of zeros into the matrix by doing basically orthogonalizing the columns in the X matrix. part of the reason I went into this idea of reflections and rotations, apart from just giving you a sense of how one does the QR decomposition, is that when we get to talking about doing an eigen decomposition to get eigenvalues and eigenvectors, or doing the SVD of a matrix, the computation actually involves a bunch of transformations that involve either these Givens rotations that I said here, or the Householder reflections. And so both doing the eigen decomposition and I think doing the SVD, it involves a bunch of these similar kinds of transformations. So it's useful to have the eigen decomposition and the SVD are both, the algorithms are both rather more complicated than some of the ones we've seen because they involve an iterative procedure. But the basic steps in doing those within those iterations are a lot of these things that we've just already talked about today. Okay, so I'll quit there and we'll pick up with Graham Schmidt next time.
I have a small question concerning the SVD decomposition. What are the conditions for on A to write, so we can write that? Is A absolutely any matrix?
I think it is. Let me remind I should have put that in here to see if. Yeah, I think A is arbitrary.
So what I don't understand is what are the values on the diagonal here? There are not the eigenvalues because some matrices don't have n eigenvalues.
I mean, you're talking about unique values, or
No, even some matrices don't have. Some matrices have only one eigenvalue. That's possible for matrices.
yeah, I mean they're really the eigenvalues of A transpose A or A transpose.
Okay.
By what I talked about over there.
The square root of the values of A just A.
Right.
Okay.
Right.
Okay,
So
but-
I mean, I believe what I wrote here is right. That the D's are non-negative.
That's absolutely right. The only thing I didn't understand was when we did over there, we did X transpose X,
Right.
and we wrote it, and there was a D square, and I think Alex said it's the square of the eigenvalues of X, but it wasn't because X doesn't X can have.
Yeah, right. A is rectangular. It's not necessarily square, and so it doesn't even necessarily make sense to. Actually, I don't even remember what are there rules for, like, can you even think about eigenvalues and eigenvectors for non-square matrices? I don't remember.
Yes, but even square matrices can have only one eigenvalue. But you can have like.
Well, but when you say have one eigenvalue, you mean that if you do gamma lambda gamma transpose, you have the same value repeated?
Yeah, exactly.
Yeah. Okay. Well, I guess in that sense, you could have the same thing happen here, and I would, depending on what you're saying of how many eigenvalues, you still have a k by k matrix. It's just the values are repeated.
Yes. Okay.
And from my perspective, from the SVD's perspective or the eigenvalue perspective of sort of a statistical interpretation, I don't really care whether they're repeated because I'm thinking of them basically as variances.
Okay.
And they just happen to be the same variance value, but it's not. I don't think it's from a statistical perspective. I'm not sure it's important.
Okay.
Mathematically, there are other implications, but
Okay. Thanks.
hold on one second.
How many calculations?